Okay, let's see an example. I think that's a very important example, maybe insightful one, hopefully. Where is the phone? Phone? Yeah, I actually like this example. I wish someone told me that example. Like, for example, in Stichenov, which is a great book, I think the first example is in page 150, 150. So it's nice to see an example before. But before doing the example, just so that we can really talk about it kind of somewhat formally, let me just remind you, that's a reminder from what you know or from what Tomer told you, and hence you know it from Tomer, is that in a UFD, so if R is a UFD, unique factorization domain, then an irreducible element, so if A is irreducible, or maybe A is irreducible if and only if the quotient of R by the ideal generated by A is a domain, those zero divisors. Right, so what's always true is that if A is without UFDness, if A is a prime ideal, then that's true. But in a UFD, a reducible element is prime. Always. In general, it's not. Prime is always irreducible. Irreducible is primes in UFDs. So in a UFD, I can write irreducible, which is nicer when you talk about polynomials. It's irreducible, you can't factor it. Easier to check. So when we are talking about UFDs, and we are going to talk about UFDs, an irreducible like polynomial, maybe if this is the ring of polynomials, will tell you that this quotient is going to be a domain. And I like domains because you can take the fraction field in the natural way, not in the weird way. Okay. And another thing that Tomer didn't tell you, but you know, or I just going to tell you now, so this is 1 and this is 2, is that if R is a UFD, then also the polynomial ring over this is a UFD. So UFD is kind of robust in this sense. It's not true for fields, for example. If you are a field, the ring of polynomials over you is a PID, not a, it's also Euclidean domain, but say it's a PID, not a field. And if you start from a PID, it's no longer a PID if you add one more variable. So UFD is one property that is preserved by taking rings of polynomials over it, which is not completely trivial. Okay. So these are two facts that you should have in mind now that we are going to look at this example. Okay, but you should really feel kind of comfortable. You should start feeling comfortable with these things. And if you don't, then I think that today we are going to. We didn't, right? We are going to post the first homework, like homework 0, not for submission, and it's kind of long, not for submission, so you don't have to do everything, but there is enough there that you can kind of catch what you don't understand and just do it. Most of it is kind of easy, just kind of refresher. Some of it is maybe more interesting, but most of it is easy. But also feel free to ask online. So is this okay? Can you digest this for now? Not the proofs, maybe just the proofs are non-trivial. Okay, so why am I doing that? Because in our case, so let's say, so this is the example, or maybe before the example. So continuing this reminder, I guess. So let's say K is a field. K is a field, like F and K are fields, R is a ring, right? So let's say K is a field. Then it's in particularly a UFD, right? So K of X is a UFD. It's even more, but let's call it a UFD. And actually, okay. And so also K of XY is a UFD. And so what do we conclude from these two remarks? So this I used the second remark, now I'm using the first one, is that if you want this quotient to be a domain, I'm taking an element, that's the little a here, but in this ring, the elements are polynomial in two variables. So if I take a polynomial, a bivariate polynomial, when I'm claiming that, I mean, from the discussion, it follows that this is a domain exactly when F is irreducible. As a polynomial in two variables, you can split it, you can factor it. Okay, I want this to be a domain, and it's kind of hard to check. How do you check this domain? I don't know, but because of this structure, all you have to do is to check that f is irreducible, which is something easy. You can do it. Like it's easy, but you can do it. I will do it now for an example. So that's why I like this connection. This is something computationally easy. Then it guarantees to you that you can't multiply two polynomials here, again quotient by f, and get a 0. That's required. I mean, if f is not reducible, this may not be a domain. So let's do the example. Now we are ready for the example, and that's we are going to kind of follow that example a little bit further next week. So it really is an example. So I'm going to take a specific f. And at some point, I'm going to also maybe fix k, but k is a field for now, any field. So let's take f of xy to be y squared minus x cubed plus x. Oh, nice little polynomial. Yeah. At some point, we are going to say that it kind of induces an elliptic curve. The zero set of this thing is an elliptic curve. But let's look at this polynomial. So, and consider the curve. I say curve, but all I mean just the zero set. No, nothing like fancy. Just all the points in the plane, maybe k is f49, whatever, for which f vanishes, namely for which this is 0, this is satisfied. Okay, so the structure of this set heavily depends on the field k. But for any k you get a set, I'm not going to kind of really write explicitly k in z of f, but k is in the background. And what I claim is that this is an irreducible polynomial, no matter what k is, I think. And so this is a domain. Okay, so let's see maybe why is this true. So my little claim is that f is irreducible. And how can you see this? Well, just by degree considerations. So you look at this thing. Actually, I haven't checked the characteristic too, but I think it's also okay. So you look at this thing and you say, if you can break it, it's going to be like, it's going to have to look like y minus g of x for some polynomial only in x, y plus g of x. Why? Because, it's y plus a of x, y plus b of x. There is no, you can't do it otherwise. And this has to be negated because there is no y coefficient. It has nothing to do with the characteristic. You would think maybe there's something to do. You can kind of convince yourself that that's the only way if this would have been factored, that's the only way you can factor. Because the degree of, think of it, you should think of x as a fixed element, or you should think of the field of the ring of polynomials where the coefficients are allowed to be rational functions in x. Then you have y squared minus alpha. So it has to be 1 minus beta, 1 plus beta. What's written here? But then you are in a bad shape. If this would have been possible, otherwise, there is a g for which this holds, and g is a polynomial in x. But then you get a contradiction. Why?
Q plus x should equal g squared.
Exactly. So there you finding a g for which this holds. The degree of this is even. Right? So again, regardless of characteristic, at some point you get paranoid about characteristics. They can do things, but not here. So that's impossible, right? So it's irreducible, which means that the quotient field here with this polynomial is a domain. So why is this what? This thing, right? Because the degree of polynomial, this is a polynomial. So the degree of this polynomial is even. And that's an odd degree polynomial, just by degree consideration. But you can also kind of try to, if you don't think about it, you can try to put a polynomial here. And you'll see that, it can't be degree 1 and it can't really be degree 2. So, yeah. But, yeah, same thing, I guess. So what I'm saying is this thing is a domain. I'm just calling it C sub f, don't worry about it too much. And its fraction field, we're just going to denote by K of f. Because it's a field, right? So we like K's as fields. So this is the fraction field. And I want to kind of play with this fraction field. Just play with it a little bit, okay? But so far, so good. I mean, we used a little bit of kind of abstract ring theory to kind of justify the fact that CF is a domain for that particular example. And I really want to kind of explicitly understand this. How do elements in K of f look like, really? Like explicitly in this example. Okay, so I'm going to kind of fix the point. So consider the point 0, 0. So sometimes we denote it by like cool 0, but I don't know how to do it on the board. So on the slide, it's like, I don't know how I did it also there, but it's like some mafcal or whatever. So look at this thing. So that point is on the curve, right? 0, 0 satisfies this equality. So it's a point on the curve. And actually, if you want, you can draw, for K equals R, you can actually draw this curve. It's a very famous one. It looks like this. Over R, okay? Something like that. It's an elliptic curve. And so you see 0 is here. And it's actually something that you do quite a lot. I mean, you walk abstractly, but you think there is a picture, right? And it's not true. There is no picture. It's F5. But you think there is a picture. And kind of remarkably, the picture, unless some weird thing happens, they may happen, actually it can conform, give you intuition, conform what you prove. This is a picture of ZF. Yeah, sorry. This is ZF for the case K equals R. Yeah. Like for F5, it's like for F5, just to make sure that we all are on the same page, I'm going to need to draw a 5 by 5 grid. And some of them I'm going to put like, maybe this is 0. I don't know where to put 0 even. Maybe this is 0, so I should put like something here. And it's going to be kind of pixelized or something. It's not the resolution will be as the resolution will go through. I mean, it's a different thing. I don't know. Curves over F5 are weird. Don't look at them. But you look at this and you think, and you take the much of what you can, you think holds here actually holds here as well. Okay? It's kind of weird, but it's more about us again than about mathematics. So 0 is a point on the curve, and all the motivation, all the discussion that we had before said, points correspond to valuations, correspond to maximal ideals, but that only holds for fields, not for curves. It does hold for curves, but it didn't. I mean, we don't know it yet. Still, I'm going to guarantee to you, if you trust me, I'm reliable, that there is a valuation. Trust me. I can't prove it because we don't have the tools yet. There exists some valuation, which we call V sub 0, from Kf, right, the field of fractional functions over the curve. Like it takes rational functions, but you should mode out every time you see an f. And the ordered set is the usual z. We have the infinity here because we had the 0 here. And let's see how much you should trust me. Yeah, and you should also trust me that V0 of x, actually, if you should trust me, you should actually, if there is a valuation and there is a value like that, you should figure it out yourself by the picture. So what do you think V0 of x? Right, so the 0 set of x is this thing, right? This is the 0 of x. This is like the if you draw not x itself, the x itself is this kind of fluid function, but the 0 set of x. So what do you think the valuation should be? 2. Because if there is some justice, the fact that it kind of touches and goes like that is a value. It should be 2, and it is 2. Okay. When you cross, for example, the valuation of y at 0 is going to be 1 because it just touches it. But the valuation of x is 2. It's under trust me, okay? I can't like explain why. Maybe over F5 it's not true because I can't draw this picture, but it is true even though I cannot. Okay? That's why I like this picture, because it gives you information that you can get it. So you should trust me on that. So that's going to be our starting point. You see, Stirtonov doesn't give examples because you can't give examples. You need to develop the theory to give examples. So what I'm doing is I'm cheating. I'm giving you a little bit of information, which actually requires a lot of the theory to prove. And we're just going to play, assuming that, we're just going to play a little bit with this notion of valuation and everything just to get some insights. Okay, so trust me on this, okay? So now let's prove, for example, I think that's the first thing I prove. Let's prove what I said. Let's prove that at least it's kind of consistent, that indeed gamma 0 of y is 1. Like, you know, if my intuition holds, then it should hold like everywhere, right? So let's look at the function y, that's its 0 set. And that 0 set kind of intersects the curve once here. Not completely clear how does it relate to anything, but once here. So let's try to prove it. Yeah, just to play with the notion of valuation and its properties.
How do you think of theoretic when informally?
Yeah, good. So you give me, say, v0, right, of a function. So I'm drawing the 0 set of that function. So in this case, it's x. Maybe x minus y is this thing or whatever. So it's, I want, and the, right. So I mean, this is a function. It lies on the curve. So at every point, there is a number, depending only on x. But if I care about how many times this function vanishes at a given point on the curve, so what I'm doing in my head, and I'm not justifying, just kind of how I think about it, but that's the right way of thinking about it, is that you should think of the 0 set of this function. That's another curve. It could be a more difficult function. That's another curve. And how many zeros this function has something to do with how many times, at what multiplicity that curve meets that curve at that point.
This means that you collide.
Yes, right. And I'm not, it will, I mean, we are not justifying nothing, we're justifying nothing geometrically in this course, but it will get more clear, the relation between the 0 set of this function and the 0 set of the curve and the valuation of this as a function over the curve. We are not there yet, just kind of, yeah, these are the right questions, but that's why Stirtonov doesn't do examples at the beginning, because I can't give you the right answers. Just like say, yeah, I think of it like that. So how would you prove that? Oh, so we have to prove that after the break. Okay, so we meet 10 past the hour and we'll prove that. Okay, so let's continue. So we had some great questions in the break. So let me just, so when we defined V0 before, it wasn't this V0. This is not a 0. This is a weird O. Okay, that's it. So V0 was over a field, and that was how many times x divides a polynomial, right? And stuff like that. Here, there is a more abstract ring going on here. And the fact that V0, so V0 is some function that I promise you exists, and I promise you its evaluation, and I'm not proving that. And I'm telling you that, you know, when it takes an element, a rational function, particular x here, it spits out 2. It doesn't mean that x squared is like dividing something, because there is no UFDness. There is no unique amount of time x will divide something. It depends on the representation. What will happen is that some ideal will be factored twice from some other, in some other ring. But for now, just trust me that there is a function that has the properties of evaluation, namely triangle inequality and additivity, and that V0 of x is 2, and that 2 came from some intuition, but we will be able to prove that 2 in like 3 weeks or something. We will need to talk about ramification indices and stuff like that, but we're going to do that. So, okay, so is it okay? We are assuming that that holds, and I want to prove that V0 of y is 1, just as an exercise in working with evaluations. And that also coincides with intuition, because the 0 set of y intersects this at one time. Okay. So let's see. So it's really kind of fun to do it. So So here's the proof for y v0 of y is 1. So we know that y squared equals x cubed minus x, not as polynomials, but definitely as elements in this ring, right? That's 0. So this means that the valuations are all the same, right? I mean, and now this thing is twice the valuation of 0 at y. The valuation of x, I told you, is 2. So the valuation of this thing is 6, and the valuation of this thing is 2. These are distinct valuations, distinct numbers. So we can use the strict triangle inequality to say that this is 2. Not usually the only thing you can say is that this thing is at least v0 of, the minimum is at least the minimum between v0 of x cubed and v0 of minus x because of the minus here. It doesn't matter, but it's here. Usually that's all you can say. But the strict inequality that we proved told us that once, if you know that this and that has distinct valuation, when actually you get equality. So, it's nice, no ambiguity. And they are distinct because this has valuation 2, this has valuation 6 because it's 3 times 2. So the minimum is 2, so that's 2. And so you see from here you get that v0 of y is 1. Right, because one of the properties that I said is this equals v0 of x. Why this is true? Good. Because y squared as an element, it's the same element as x cubed minus x in this thing. Yeah. It's like, yeah. Okay. So that's kind of, you see, it's kind of nice working evaluations. It's very easy to get valuation of, I don't know if it's very, here we really relied on the fact they are distinct, but it's kind of easier. You don't work with rings per se or ideals or something. That's something that you do when you do number theory. With the valuations, it's kind of a nice machinery to figure out what are the 0 and whole order of some functions, if you know other functions. But we're going to do more than that. Now I want to kind of get away from this point 0, 0 and just try to really understand how this looks like. I mean, what is it really? I mean, what's going on here? Maybe I should say more about it. So even let's move here. So what are the elements here and how should you think of them? So k of xy before the quotient, just all the polynomials. And polynomials induces functions, but maybe not the way you think. I mean, it could be the case that the same polynomial induces, a different polynomial induces the same function in a finite field, right? So for example, in fq, in a finite field fq, xq minus x is always 0, right? That's in fq, every x that you plug to this thing will give you 0. So this means that this polynomial as a function in fq is the same as this polynomial as a function. It's not the same function. It's not the same polynomial because x to the power q is not, formally, it's not the same polynomial like that. But if you only consider it as a function over fq, then it's the same polynomial. Put differently, because we know evaluations are homomorphisms, the fact that this polynomial and that polynomial, after you apply the evaluation homomorphism, you get the same thing, it doesn't mean that the original thing was the same. So it could be the different polynomial gives you the same function. Different polynomial could give the same function. Here it gets even more messy, because here, for example, y squared is the same polynomial as this minus that, x cubed minus x. It's not the same polynomial. Sorry, here it's the same polynomial in the sense that it's the same formal element. Right? The formal element y squared is the same as the formal element x cubed minus x here. Every time you see a y squared, you can replace it by that. Even before evaluation, just because this thing is 0 in this thing. So here, the ambiguity between functions and the polynomial representative holds even before the evaluations, even before the functions. It holds between the level of polynomials and the representative in this ring. So this is what happened here really. Y squared as a polynomial is not the same thing as this, but as an element in this ring, it is the same. It's kind of interesting. What you can show, unless I'm mistaken, I hope I'm correct here. Don't take my word for it. Maybe there is some asterisk, but I think it's fine. Is that if you take two distinct, because this is irreducible, if you take two distinct elements here, they will give you two distinct functions. Good. So Tomer said yes, so I'm fine. Happy. Right. So two distinct elements here, which are just formal elements, x squared minus whatever. If you are going to think of them as functions, then you are going to evaluate them over the curve. For distinct elements here, you get distinct functions. So this means that you should think of this as the ring of polynomial functions over the curve. So this is a thinking, not a, right? You can formalize that. This is the ring, because it's a ring, of polynomial, this is how it's called in some functions. You see, I kind of, these are two loaded words, polynomial and functions, these are different things. But over the curve ZF, so because the distinct elements here, like y minus x, whatever, if they are not the same in the ring, they will yield distinct functions when you evaluate them over the curve. If they are not the same as elements in this ring, there will be a point on which they will disagree when you evaluate. Okay? So in other words, you can think of it as the ring of polynomial functions over. I'm not sure you ever made this distinction. I mean, even in the original world, like polynomials in one variable, you had polynomials and you had functions. And for example, in coding theory, you care about them as functions, you evaluate them, but you analyze them in terms of polynomials. So there is this gap between functions and polynomials, and here it's even between polynomials and the representative. And then there is also the function level.
So can we think of K as a finite field?
Yes.
Okay, so you have infinitely many distinct elements.
Here?
This ring of polynomial functions.
Here. Before that. Yeah.
No,
Also after that. Okay. Well, yeah. Yes. And you're saying the only finite number of functions?
Yeah.
Oh, that's so. That's weird. 1 second. Yeah, good. So thank you, Itai. Right. So what I said I'm not sure about is incorrect. It should be only one case that maybe at least infinite, but definitely when it's algebraically closed, what I said is correct. Right. There could be in other words, even if K is finite, the point that will make sure the function is different could be in an extension. I mean, for example, ZF could be zero, the zero set, actually.
Okay, but so also the problem we had before, like with tuple in this
Yeah.
Over a finite field, they are not the same. Over
infinite field. Right. Infinite field, you don't have this problem. Right. You wanted to say the same?
בהמשך מה שהוא אמר, אז מה מיוחד בזה שזה פתאום פונקציות, כי גם במקרה הזה זה באקסטנשן כלשהו. זה כאילו מיוחד בתוך.
I mean, what's special is that it could have been the case, even if you work with infinite field. I mean, it's not, so I can't argue that, but potentially it could have been the case that like distinct elements here give you the same function. It's not clear that it's not the case, even if the field is infinite.
But what I'm asking is, why is this the ring of polynomial functions and the regular ring of polynomials is not the ring of polynomial functions?
Because no, but there y squared, I mean this thing, right? Here y squared is a different polynomial than the minus of this, but it's the same function here on the curve.
So it's like xy is the polynomial function on the plane, and now we restrict only polynomials.
Yeah, I don't understand the difference in them being functions or not functions.
So y squared is as an element here. Let me know if this is an x cubed minus x as an element here. They are distinct elements. Here they are the same elements. Right. Here. Right. So what I'm saying is that you could say, why not? That's what I thought you were saying. Why don't you call this the ring of polynomial functions? Because different elements here could give you the same function.
Over ZF, yeah.
Yeah, but that's what I get over ZF. Because the evaluation, so that's what Thomas said, You only evaluate here. Yeah.
The word ZF.
Yes. Yeah. But good. So should I recap or do you have concrete question? I can just. All right. So good. So you can look at. So let me just. You can look at these two elements, and you can look at them in two ways: either as elements in KXY, or as elements in CF, the quotient. Right? So let's look at them as elements in KXY. These are two distinct elements in KXY, because as formal elements, because there is no Y here, there is no XL. So these are distinct elements. But and indeed, if you're going to evaluate them, so K is infinite, sorry, as I said, or algebraically closed. And so if you're going to evaluate on the entire plane, you're going to find a point in which they disagree. But if you're going to evaluate them only on ZF, the zero set of F, you're always going to get the same answer. Right? Because, right, they're the same function there, like this. Because y squared on ZF, by the definition of ZF, always equals to that. Right. So as functions all restricted to ZF, they are the same element. And I don't want that. I don't want that distinct formal things will produce the same function. Because I want to argue, I want that when this, so I wanted them to be identified as functions if and only if they are identified as formal elements. So if I take them here, you see they're not the same as formal elements, they're the same as function over ZF. But that's fair. I mean, there is no, ZF is not encoded here. But this is the exact ring. Well, that's more to say. But in this ring, these two elements, well, still they are the same. As functions, they are the same on ZF regardless of where you think they are. But in this ring, they're also the same as ring elements.
I think these are the same as ring elements in CF. It's like the definition of being of like.
Right. It's like obvious, like. Right. What's the point? Right. So the point is that, I mean, these two as functions, they agree on ZF as functions. Right. This is the point.
Function on CF, this is the new thing.
Right. Exactly. So I want a ring such that the elements that you're going to evaluate are going to agree exactly when the function as functions they agree. And here it's not happening, and here it's not happening, and here it does happen. Right.
Like these two elements they're obviously the same in CF.
Right.
As objects.
Yeah, like formal elements.
They are not obviously the same, and you claim that they are the same as objects, it's functions.
I think that it's obvious that they're the same, but yeah. So the point is right. Oh yeah, good. So right. So we are going to develop the theory regardless of all of these remarks. So it's not going to matter. But what will happen is that there's going to be a point. I mean, the way we are going to define the place is going to also encode the points in field extensions, because the place is going to be a maximal ideal of this ring, and maximal ideal of this ring will also encode points in the extensions of K. They're going to be conjugate, but going to encode them. So the fact that we are working with a finite field K won't matter to us. There's always going to be infinitely many maximal places, maximal elements, which are going to correspond to points in field extensions. So we are going to kind of, in a sense, bypass this problem altogether. But I just want to say that these right. So I want things to be different as functions if and only if they are different as formal elements. Yeah, maybe I don't know. So you know what? Maybe let me just continue and still continue with this line. So let's see. So actually, so we are exactly going to do that. So let's try to understand KF. So let me tell you what I mean. So seems like it's a yeah. Oh no. Okay. Okay. So what I'm claiming, obviously, is that every element in KF can be written as, I mean, every element in CF right? It's a polynomial, but you have this quotient. So in particular, you can say every time I see a power of y which is 2 or larger, I can replace it with x's. So I can always write it like that. So that's a general element in CF, right? So as a fraction, that's a general element in KF. Not unique. Good, and then we are going to see good examples like that. And I want, it's not going to be unique, but I want to give it some kind of, not unique, but some way of canonicalizing how we write it. So the first thing you can do is you can remove this y. How can you remove this y? Like how can you get another expression that doesn't have a y down there? Exactly. So this is general element, but we can always do like, let me write it like that, without the x's. You know what, it's so, I don't know, let's not do it. You can do it like that. I mean, you can say, wait, you cannot do it because maybe this function is 0. I mean, maybe that's going to be 0 at some point on the curve, but I'm not doing it as functions. I'm working in terms of formal elements, so I can definitely do that. At some point, maybe evaluation issues will come up, but that's formal elements, that's the same. And that will give you, once, so here you're going to get cx squared, no y's, and you get a y squared, but the y squared you can replace back to a polynomial in x. And so at the end of the day, you can write it like that, where these are rational functions in x. Right? So these two are now in k of round brackets x, rational functions, which are coming from what you did here. Good.
The claim here, like to reduce it to rational functions,
Yeah. Right. That's what I'm using like quietly. I want to continue to develop this for a second, though. And just say, well, I think we had this discussion here, but it had nothing to do with what's written here. Maybe I should just skip the definition of CF on the board. And this is y squared minus xu plus x, I think. And then kf is the fraction. It's great questions. Thanks for the questions. I hope I'm answering it well enough, but keep asking. And so let's look at the valuations. I'm still with the zero valuation, but let's look at the zero valuation of an arbitrary element in KF. And we just said an arbitrary element in KF can always be written like that. So let's take an element like that. Right, you take the valuation at 0 is a function from KF, and every element in KF looks like that. So I'm just looking at this thing. And from the triangle inequality, I know that this is at least the minimum. I mean, there is no much point in where I'm going, by the way. You should maybe think there is. I'm just kind of playing with it, but you'll see something. The minimum between these two numbers, between the valuation of this and the valuation of that. But I know that the valuation of this thing is what? Exactly. It's v0 of b plus the valuation of y, which we proved to be 1, assuming the valuation of x was 2. And now I claim there is actually an equality once I see that. You see, we know that the valuation here is at least the minimum between the two. But you see, x had valuation 2. And if you think about it, it would mean that any polynomial or rational function in x will also have an even valuation. Because it's just x squares. You have only 2's there. So these numbers, I don't know what these are. This number and that number or that number are even. So this is an equality because that's odd. So actually what we know now is that in this ring, kind of nicely, you can express every element like that. And having done so, you know what the valuation. The valuation is just the minimum between v0 of f of x and 1 plus v0 of b of x. It depends on a and b, of course. Other than that, it's fine.
The fact that this, even this is on, makes the inequality correct.
Exactly. Right, it's cool, right? I don't know, right? It's kind of, you don't really like understand what you're doing, like you don't look at the points or the maximal ideas, but you just have this like arithmetic of valuations that gives you something. If you take it back to like polynomials or primes, then you're going to say, here p appears to the power fifth and here to the power 2 and something like that. But you don't need to. The valuation is the language to handle these things without looking at the elements themselves. So let's do some random example. We are in an example, but let's go even lower. I don't know, deeper is the wrong, like lower. So let's look at the valuation of just an exercise. So what do you think about this? That's an element, right? It's a of x plus y times p of x. It's an element. So I have -2 here, I don't know. So let's see. Okay, so good. So it's the minimum between the valuation of 1 over x and valuation of y. And that's -2 because the valuation of x is 2. And this is right, this was 1, so that's -2. And you can feel there is a pole here, right? Like there's a 1 over x and y is like poleless, so at 0. So I don't know why I did the other example. Is there a reason? So maybe let's not do it. But let's consider another thing. So let's look at v0 of x over y. And even before that, let's just look at x over y. Just consider that. Forget about the valuation. Or I'm asking you, over the curve, is it defined at 0? I mean, you can say, well, I don't know, it's like 0 over 0. So exactly, good. So very good. So it's stronger. The x0 is stronger than the y0, right? So generally that's true. I mean, I proved for products, but also for fractions because of the minus. And that's a 2, and that's a 1. So that's a -1. That's a +1. So you get this has a pole, but this has 2 zeros. I mean, this has a 0, so you have a pole, but this has 2 zeros, so you're fine. And you can say, I don't know how you feel about it. I mean, I kind of gave you this fact that v0 of x is 2, and you're basing that on that, right? So if it was your life, if you had to evaluate this, if you have, there is a pilot and you're in a plane, I don't know what you have in mind, and you need to evaluate it to know if you can evaluate it or not. Oh, jeez. So what can you do? Well, Gil told me that v0 of x is 2 and all of these things, but is there like an easier way to see it? And that's the nice thing. I mean, is there another representation of the function x over y that without this machinery will convince you that the answer is 1? And there is. And so you can write x over y as y over x squared minus 1. You see, because in this ring, y squared equals x cubed minus x. And here you are convinced, right? Here it's fine. You can plug 0 to x, nothing happens. And you can apply 0 to 1. At least you can plug it, but it's indeed 1. Right, so that's what I said about UFDs. I mean, you don't have unique factorization, so a function can be written in several ways, and at a given point, one way can be kind of more instructive or informative than the other. And valuation don't care about that. See, the valuation knew that, in a sense, without doing this thing. And that's kind of the power of it. It works in the right level, not in the level of functions, but in the level of ideals, in a sense, and we'll talk about it. Yes. I don't know, yeah, because here you kind of use my given hint that v0 of x is 2. So you need information from me, like as a human being. Here you can kind of convince yourself, well, that's true. And when you plug 0 here, you don't get 0, and clearly 0 is not a pole of y. So that's going to be 0, maybe with higher multiplicity, but at least It's not going to be undefined. And from here, you really needed my extra bit of information that v0 of x is 2.
Why do you like substitute 0 to it? Like what?
Here you can substitute 0 easily, right? Why am I doing this here? Right. No, good. Because the question is this the function defined at like the point 0, 0? So can I plug 0, 0? And here you can easily see that you can plug 0, 0 to get a number rather than an infinity or undefined. And here it's not obvious to see, I think. It's the same function. These two elements are the same function in CF. So what I'm telling you is that here you can definitely plug 0 to x and y, and here you can actually do it and get a number, and here you can't. I think you plug 0, 0, you get, I don't know what it is. When you plug 0, 0 here, you get a 0. That, right, so what I ask is this defined at the point 0? And from the valuation point of view, you can see that you get a 1, so it's not only defined, it actually vanishes there. And from this representation of the same function without valuations, you get that actually this function, which we just write more nicely like that, not only defined, but actually vanishes at 0. That was my point.
You get information for the valuation of constant, not function.
Good, that's exactly what I'm going to do now. How do you know that? Very nice. So that's the exact thing I'm going to do now. Thank you. Where is it? 7, 26, after 26, you have 27, right? I skipped 25. That's the, okay. So actually what you asked was before what I said. So good, so let me do that. So what happened to constants? So what do you think should happen to constants? Valuation 0, right? Because exactly a constant, unless it's 0, of course, has no zeros and has no poles. And I don't know if you walk over a curve or whatever, a constant should still be defined. That's very weird that 5, you cannot evaluate 5 at some point, regardless of what your geometry is, right? So what we are going to prove in this example, but it's in general, that the evaluation is going to be 0, namely 0 means no pole and no 0. Like, it's another 0. So let's see. So let's say we're working over a finite field now. You can do other things, but let's just do that. So what is v0 of z for some z here, which is non-zero? Of course, the valuation of 0 is infinity, because 0 it has infinitely many zeros. So you give me 5, you give me some z which is non-zero, and I want to prove that this is 0. Let's prove that v0 is 0. Namely, but you can replace this 0 with anything, like the valuation, any valuation at z would be 0, but let's just stick with that. So the point is that you have this thing, right? Z satisfies this equation, and so you can apply your valuation to z or to z to the q, and then what will happen here? Exactly. And now you can say, whoa, but this is 0 because this is the, divides by the characteristics. But we're over z, the integers here. No, we're not over the field. This thing is over z, right? So when you have q times something equals something, that something must be 0. Okay? That's a kind of cheaty way to prove what will be more general in later. This no, I didn't use. This proof holds in general. Why?
No, for the minimum, to say that the minimum there is even.
You are correct. Yes, and that's why I did this before I did that. Good. So let me just. You're right. So I cheated actually when I said this equality. I kind of assumed that you're right, that the coefficients in the polynomials have 0 valuation, because the coefficient in the polynomials. And it's also a coefficient for me in the free term, if they don't have valuation 0, then I actually can't argue this, because the coefficients will also have valuations, right? You look at 3x squared, so the valuation of this is the valuation of 3 plus twice the valuation of x. But unless this is 0, what I said is incorrect. So yeah, so that's why it appears in page 25 before this, and you're right, and actually use that without noticing. Sorry, yeah. Good. Yeah, good. You catch me. Right. By the way, if you want to prove, I think it's one of the exercises or something. If you want to prove that CF is not a UFD, I mean, we talked about the fact that there is this, the fact that it's not UFD allows for several representations. That's not a proof. I don't know. To prove that it's not a UFD, you need to prove that there is an element with two distinct, like truly distinct representations. So as an exercise, try to prove, I mean, here is an exercise. Prove that CF is not a UFD. Namely, the problem is real. You really cannot factor the numerator and denominator and say, aha, the valuation, because there are many ways to write things down. So, for example, in this case, the hints, there is a hint, actually the obvious hint because it's the only thing you know. Just look at y squared equals x squared minus x cubed minus 6. When that holds in the ring, and you can write this as x minus 1, x plus 1. And what you should check is that these are two distinct, namely not just up to units, distinct factorization of the same element, making this not a UFD. Right? I mean, 2 times 3 is minus 2 times minus 3, but it doesn't mean that Z is not a unique factorization domain. It's just because I cheated and put minuses, put units. So what you need to prove here is that this is really are distinct, namely the things here are primes, and it's not there is a unit transformation that takes one to the other. So if you want to brush up on UFDs and stuff like that, it's not going to be crucial to us. But if you do want to do that, then that's a good exercise. It's very easy because all of the polynomials are degree 1 here and so forth. But you can do that. I feel like this is the part of the course where I gave a kind of, in a sense, a premature example. So it triggers some like lack of understanding by definition, and also I'm not really bridging between the algebra and geometry. So you see the curve, and I tell you a function as valuation. It's not clear what I mean. It's going to go away. It's going to be really just abstract from now on. So I think that you will definitely. Everything is going to be understandable, like no like ambiguity from now on. But in this example, because I wanted to give an example, there are, aside from the questions that you should have asked, there are these questions that you can't avoid asking, but they are going to go away. Not because we are going to understand it, just because we are not going to talk about it. But in a proper course, if I had like 20 weeks, I would have taught the geometry as well. Okay, and then it would have been better. But nonetheless, any question after that motivating speech about no questions? Any questions?